this video, we are going to investigate the basic concept of the field-oriented control algorithm throughout a so-called system effect diagram. You can see the PMSM motor in the bottom part of the effect diagram. This is going to be the main part of the so-called plant model that we shall control. We are going to assume that it is a surface-mounted PMSM motor with only a synchronous torque component present. The hardware equipment that is going to control the PMSM is the three-phase PWM inverter. We shall develop such a function software that is able to control the PMSM motor with the help of the three-phase inverter to fulfill the requested speed or even position that the user or some higher software component demands. First things first, during the FOC algorithm, we shall measure the phase currents of the motor with the help of a shunt resistors and use a so-called low-pass filter to filter out any background noise that is unnecessary for us. The latter low-pass filters are marked with the letter F on the effect diagram. It is our free choice that whether we would like to measure only two phase currents of the motor and calculate the third component, or measure all three phase currents at the same time. By utilizing the Clarke-transformation, we shall calculate the current components in the XY coordinate system. This coordinate system is going to describe the measured three-phase currents in a time variant two-phase current system. During the Clarke transformation, we are going to use the actual electric angle of the rotor pole flux as an input to calculate the actual direct and quadrature currents present in the system. Note that these direct quadrature current components are fictive representations of the three-phase current system of the PMSM motor. Their only intention is to ease the work of the proportional integral regulators by describing the AC three-phase physical quantities as DC components in the TQ frame. By implementing a simple derivative function, we will be able to synthesize the angular velocity of the rotor by firstly measuring the angular position of it with the help of an appropriate encoder. This mathematical correlation between the angular position and velocity is represented by a d divided by d2 block in the effect diagram. This angular velocity signal is going to represent the actual speed of the rotor, which will be further used by the speed controller. The speed controller is responsible for determining the requested torque in Newton-meter dimension for the FOC algorithm based on the requested and actual speed inputs. By knowing the motor parameters, an exact analytical equation shall be used for the calculation of the requested quadrature current component based on the requested torque value. As you may remember, the quadrature current is the so-called torque-generating current component of the control algorithm. Since we have assumed that the plant model we would like to control is an SPMSM, so a surface-mounted permanent magnet synchronous motor, during the overview of the FOC algorithm, we can assume that the direct reference current is equal with 0. Later, we are going to shortly discuss the possible effects of the non-zero direct current reference values, but for now, let us assume that it is equal with 0. The current regulators of the direct and quadrature directions shall output reference direct and quadrature voltage values. As you may know, the effective control signal in case of a motor drive is nothing other than the voltage itself. Hence, our goal is to determine an average phase voltages for the PMSM motor in order to achieve the requested torque, speed, or even position values. All in all, the FOC algorithm is alternating the actual average phase voltage values with the help of the implemented current control loops. After the reference direct quadrature voltages are being calculated, an inverse Clarke transformation is performed in order to get the reference phase voltages. Note that for the inverse Clarke transformation, the angle of the rotor pole flux is also needed. From the current in the XY plane, the A, B, and C phase currents can be calculated with the help of Clarke transform. The SVPWM algorithm is responsible for utilizing the available DC link voltage in the most efficient way possible. For this, we are going to get familiar with the basic scalar equations needed for determining the final requested phase voltage values. This method is the end of the field-oriented control algorithm altogether that we are going to cover within this course. A so-called platform software is needed to transfer the requested phase voltage values to actual EGBT switching signals in the three-phase inverter. The gate driver hardware component is responsible for driving these previously mentioned IGBT semiconductors according to the low power control signals coming from the microcontroller itself. However, in this course, we are going to use software in the loop, so SEAL simulations, for the validation of our FOC software. Hence, the gate driver is not going to be a real part in our simulations. Finally, I'm going to give you a previously built plant model that we are going to configure together, containing the three-phase voltage inverter and PMSM motor as well. This is simply needed because the implementation of the plant model could be an individual course content altogether. In the previous slide, we have seen how a typical field-oriented control algorithm looks like, considering block diagram representations. However, there were several abbreviations that hasn't been clarified yet, so let's summarize them within this slide. The PMSM is the control plant model that we are going to model in Simulink before the creation of the function software. The F is standing for the filtering process, or in other words, the signal conditioning regarding the phase current measurements. I have marked with the letter P the position sensor attached to the PMSM motor, which could be a sine, cosine, or even an incremental encoder when we are talking about an FOC control. The pi omega is representing the angular velocity, the pi psi is representing the pole flux, and finally the piid and piiq are representing the proportional integral regulators. Below these regulators, you can see the needed Clarke and Park coordinate transformation representations. During the upcoming videos, we are going to dive into the details of each block representations, describing the mathematical behavior of them to find out how it is possible to implement these algorithms. Stay tuned, because in the upcoming video we are going to discuss the typical waveforms for the FOC control method.